Good afternoon. Thank you everyone for joining our seminar today. For your information, the seminar is being recorded and will be made available on the RemPlex webpage in just a few days. As a reminder, we request that you please keep yourself muted during the presentation and Q&A. And we also encourage you to rename your participant profile to your actual name if you like. If you hover over your name with your cursor, you can change your participant name to your full name. My name is Alicia Gorton with Pacific Northwest National Laboratory, or PNNL, and I'll be moderating today's seminar on behalf of the Center for the Remediation of Complex Sites, or RemPlex. RemPlex is a PNNL platform that couples unique core competencies with expertise and state-of-the-art facilities and physical assets to develop, mature, and deploy advanced technologies to solve complex issues of contaminated subsurface environments. Today's seminar by Katie Muller and Mike Truex of PNNL will discuss the transition between remediation elements, in particular from active to passive remediation. Katie Muller is an earth scientist at PNNL. She received her PhD from Tufts University in Environmental and Water Resource Engineering and completed postdoctoral training at Oak Ridge National Laboratory. Katie joined PNNL in 2019, and her research focuses on experimental and contaminant fate and transport modeling to understand, predict, and inform subsurface remediation. Mike Truex is an advisor at PNNL in environmental remediation and serves as the Deputy Director of Environmental Remediation Applications of RemPlex. His experience includes work at Department of Energy, Department of Defense, and private remediation sites. Major programs include support to the DOE Hanford site, providing technical and programmatic support for assessing and implementing improved remediation and characterization technologies. During and after the presentation today, I encourage you to submit any questions you have via the chat box, which will be monitored, and the questions will be passed along to Katie and Mike for discussion. I'll also be posting a link in the chat box to a RemPlex survey that we invite you to participate in to provide feedback on today's seminar and offer recommendations for future topics. So with that, thank you again, and I'll turn it over to Katie to kick us off. Katie?
Thanks. Okay, so today Mike Truex and I are going to be discussing some of the evaluation approaches and considerations surrounding the transition from active remediation over to passive remediation. So first, just wanted to give a brief outline of the topics we will be covering today. So I'm going to start us off by providing some of the basics of transition assessments, so including why a site might want to move from active to passive treatment, when it's appropriate to consider and complete such a transition, and then how a transition assessment might be completed. From there, I'll go into more of the decision framework that's really been built up out of adaptive site management and see how we can specifically apply that to this active to passive transition assessment. From there, I'm going to cover some of the existing tools, methodologies, and calculations that can be used to help to build this technical justification around our assessment. And so after I provide kind of this more broad overview, I'm going to hand it over to Mike, and he's going to walk through two different case studies to provide some insight into how such an assessment could be completed at a field site, while highlighting some of the complexities that need to be considered. He's also going to discuss some of the additional steps that need to be taken into account after a transition has been completed to determine if risk is still successfully managed at the site. So the main driver behind moving into more of this adaptive management stance with the potential goal of transitioning from active to passive treatment is that remedy cost, timeline, and risk has this potential to be more effectively balanced under a less active remedial approach. And so while active treatment may be required during those early remedial stages in order to quickly reduce our contaminant mass or decrease that mass discharge in order to protect those target receptors of interest, in general, active treatments tend to be far more costly than their passive alternatives. And so this really is circling the question of, well, how much mass can we leave in place? And so in this kind of regard, there's a few broader aspects to consider around this idea. So first is that residual mass really only constitutes an unacceptable risk if that exposure pathway is high. And that additional mass removal doesn't always equal risk reduction. So further on this point, the goal of remediation is never to remove 100% of our contaminant mass. And so sites have this inherent complex balance between treatment requirements, duration of the proposed remedy time, and remediation costs. And so there may be this opportunity for considering an alternative, potentially less active approach to manage that site into the future. And so this leads to the next question. When may it be appropriate to consider transitioning from active to passive? And so there are kind of a few clear signs, at least, that a transition assessment should be looked at or initiated. So first, if the previously agreed upon condition has been reached. So for instance, if your remediation is going very well and going as planned, and that source strength, the plume behavior, the mass flux, or any of those other site metrics have been successfully reduced or managed to your specific regulatory levels, then this would warrant potentially altering your current remedial approach and kind of bumping it down to one that's more passive in nature. On the other hand, if your remediation has begun to kind of stall out and it provides less and less treatment over time, or if your remedy has become impractical for whatever reason, it may be also an appropriate time to reevaluate your remedial plan. And so field data can provide some insight here, in specifically when looking at the remediation efficiency, in order to determine if your site is really, or your remedy is heading towards that diminishing return behavior. And so this figure here, as we move along that mass removal curve, we may enter this point where remediation is just becoming less and less effective, and it may be time to consider an assessment or an alternative. So similarly, if your site objectives change, so this could be because the site conditions actually warrant a TI or a technical and practicality evaluation, or development of an alternative remedial action objective. Now, this would be another reason why you may initiate this transition assessment. So then the next question really becomes a little bit more technical in nature, and it really relates to how we would complete such a transition assessment. So the decision framework outlined more in the adaptive site management literature can really be utilized specifically for this transition from active to passive treatment. The adaptive site management framework can give us this structure while taking into account the site uncertainties. It also provides checkpoints that we can use to reassess that the transition is fulfilling the site objectives as kind of desired. So I really just wanted to put up this slide to point to the many recent guidance documents that are out there that focus on adaptive site management, remedy optimization, and end states, because they're really excellent resources that can provide some further detail into kind of this overall decision-making framework. So using that adaptive site management framework, we have kind of defined a framework specific for these transition assessments. And so the first piece here is really to refine your site conceptual model. And the important point is doing this from the perspective of passive conditions. So this first step really includes identifying those key and controlling processes that will exist once your active remedy is shut off. The second aspect to this is to determine if the current site conceptual model is sufficient to capture the site complexities and uncertainties that will be important under, again, those passive conditions. In certain cases, an update to the site conceptual model may be important to better reflect the updated site conditions, not only in terms of remaining mass and location, but again, to identify those key processes and features that will control the overall contaminant feed and transport at a site. The next step is to look at the site objectives. And while this has likely already been accomplished previously, it is important to have a good grasp on the potential exposure pathways, especially if there's this possibility that those could be altered under passive conditions. So again, here is another point where you should evaluate that remedial action objective concentration, as well as some other site considerations such as the time and budget. The next step is to predict or estimate passive remedy performance. So again, the overall idea here is to quantify the potential impact of the remaining mass. So this can be done through estimations of total mass, mass flux, and attenuation processes in order to provide really this overall picture of the contaminant fate and transport that will occur once that active remedy is shut off. And so in many cases, this means attempting to estimate those rates, those metrics, subsurface conditions while your active remedy is still operational in terms of what that looks like for passive treatment. So there's a wide range of different tools and methods, and really your best option for a site may depend on how complex your site is, as well as how well characterized it is. And so this really ties into that level of uncertainty. And so these methods can range all the way from kind of more of a bulk estimate, kind of a back of an envelope type calculation, all the way on the other side of the spectrum to this full-blown multi-phase 3D contaminant fate and transport type of modeling here. And so I'll touch on some of these various tools in a little bit. But in terms of this process, it would be at this point, after establishing that strong technical justification for transitioning, that transition from active to passive would occur. So from here, you want to monitor those key performance indicators, that being concentration, mass flux, and attenuation processes, in order to determine how accurate your passive performance predictions really were. And then also, of course, to ensure that you are still meeting your site objectives. And then the final piece is kind of this reevaluation. So if your field conditions differ from your predictive modeling parameters, then that site conceptual model may need to be updated and refined to reflect the actual processes that are occurring on the site, again, under passive conditions. And so these last three steps can be iterated over if needed in order to help determine if your remedial active action objectives will likely be met into the future. So really this framework boils down from a technical side to trying to estimate the potential site impacts of that remaining mass. Or more finely put, does the aquifer attenuation provide the necessary reduction in your contaminant concentrations as to balance the mass flux in order to meet your required threshold concentrations at your regulatory location. And so kind of the first piece of this is to look at the source. So, the first step would be to estimate the remaining mass in place after your active remediation is complete or terminated. And this can be done by conducting an inventory of all of the contaminant mass in terms of where that resides within the subsurface. The mass estimate kind of illustrates the overall magnitude of the contaminant problem in each of those contaminant zones. And so there are various methods that can be utilized to estimate the remaining mass. Again, they range from rather simple methods. So one of those more simple methods would be to take the average concentration and multiply that by the total affected volume as a mean to estimate mass. There's also this method of creating ISO concentration contours from field data to estimate residual mass, and this is done through the application of partitioning coefficients. And so, of course, these mass estimates can be increasingly resolved and refined through additional sampling in order to reduce some of those uncertainties if needed. But it's really kind of this inventory that gets paired with estimates of your mass discharge or fate and transport modeling that will help us estimate the source duration, or really its longevity, that will be needed when we weigh in for our overall decision making. So field data can be used to estimate mass discharge or mass flux. And so really the benefit of the mass discharge is that it can be more easily compared to the attenuation capacity and really rolled up into an estimation of the down gradient transport behavior. So mass discharge can be calculated from groundwater data and knowledge of the Darcy flux. And so one common way to do this is through the transect method. So this method can utilize either existing well networks or additional wells can be installed to create a specific transect of interest. Mass discharge can also be determined through pumping tests, where the difference between the natural gradient and the induced gradient can be reconciled through calculations and assumptions about the flow conditions in the subsurface. If the active treatment in question is pump and treat, then your system is likely already doing this, and that data can be utilized in this assessment. Another field method that can be used is passive samplers. So these can be installed to pinpoint the flux at a desired location as well. And then the last piece on this is rebound testing. So because the impact of active treatment, such as pump and treat, on groundwater flow patterns or interpretations of that plume behavior or concentration distributions, these can really be facilitated by conducting a contaminant rebound test as to better mimic the behavior that will likely occur under ambient or passive conditions. This type of testing can also help identify if matrix diffusion could potentially play a role in the site in the future and if that needs to be taken into account. So the last thing I want to say here is, of course, all of these evaluations require professional judgment. So for instance, if there are steep concentration gradients or wide variations in concentrations across plume, then maybe a concentration-based approach may be more appropriate than a spatially average mass-based approach to evaluate that down gradient behavior. So a little bit further on this, if there's high uncertainty in some of the parameters despite best efforts at characterization, you might have some uncertainty when it comes to transitioning. Heterogeneity will also tend to increase some of those uncertainties. So while we don't want to be overly conservative, there is really this need to take into consideration that uncertainty into our estimates and see how they get folded into our calculations and ultimately into our decision making. So the complement to estimation on those source terms is the natural attenuation rates and capacity. So there are many processes that will really decrease the concentration, those contaminant concentrations along the flow path. So these could be processes such as mixing and dilution. They can also be contaminant specific properties or processes such as absorption or degradation. And so field data can be used to estimate kind of a bulk attenuation rate, for instance. And so this can be done by looking at the concentration versus distance data as you kind of move away from the source. Tracer tests can also be used to estimate the non-reactive processes through comparison of the tracers and the contaminant behavior. And then actually laboratory testing can play a role here as well. And so some of this testing can kind of quantify our potential for biodegradation, for instance, through either various isotopic analysis or microbial analysis. So for instance, with microbial analysis, we could determine what communities are present within the aquifer, at what abundance, and what the potential is for biodegradation. So with all the information about the source and the attenuation, these elements can really kind of be put together to help us determine those impacts of the residual mass. So conceptually, this assessment really is, again, to see if that attenuation behavior can decrease your mass flux enough to get it below those site goals or that regulatory level of interest. So all the information gathered on the source and the attenuation can be utilized in a threshold type calculation to estimate and compare to those actual site conditions. Of course, this overall concept can be improved through more complex fate and transport assessments and modeling as well. So while I touched on some of these approaches in a more general sense, I also wanted to provide some of the existing tools that are already out there. So there's various tools that can help estimate those source terms in terms of the mass in place, and then also completing some of those mass flux calculations. And then on the transport side, there are a wide range of either numerical or analytical models that can be used to estimate the likely attenuation and then ultimately the down gradient concentrations. So of course, this is not an exhaustive list. And actually many of the tools that I've listed here have come out of Department of Defense research and funding. And so, so these tools are really more specifically focused on those DoD contaminants like the chlorinated solvents and organics. However, of course, generic fate and transport modeling can, regardless of the contaminant of interest, be built to your specific site needs as well as that desired site complexity and kind of tackle any of those heterogeneities and assumptions that go along with that. So from here, I'm going to hand it over to Mike, and he's going to walk through how some of these approaches and methods can be used at specific sites to make some transition assessments.
Okay, well, thanks, Katie. So given that sort of background and context, what I thought we'd do now is move to some case studies and some discussion that talk about some of the ways that we can think through active-passive transitions. And on this slide, I want to bring out a couple sort of starting points to talk about. So one is this idea that if we're going to make a transition from active to passive remediation, during that active phase, of course, we've been acting on the subsurface with either pumping or some sort of treatment. So in this once we make the transition, there's going to be transient conditions. And so we have to recognize that in terms of how we analyze the situation and do our verification monitoring. And then as Katie pointed out, that this active passive transition really centers on this idea of balancing the mass in the source area or the area that's contained or treated, and then what's balanced by attenuation. And so when we think about that, we've got either a residual plume that we want to now leave to passive remediation or some source material that we want to leave. And for attenuation, we think about those in terms of attenuation rate. So, what sort of processes are occurring. But to turn that into an attenuation capacity that can balance a source, we really need to think about an attenuation zone. So what is the size and the time frame that we can allow for those attenuation processes to occur? Because that really helps us define that overall capacity that could balance what we have in our remaining source material or plume. And so talk a little bit about that in terms of some case studies to provide some examples. And then also I want to talk a little bit about this need for verification monitoring, because like any decision, even when we start with selecting the remedy in the first place, we have to verify performance. And so that's going to be the same thing here. If we decide to do a transition, we're going to have some sort of verification. So I'll touch a little bit on that and provide some examples to help illustrate that. So to kind of reiterate this idea, when we think about the balance between source, strength, and attenuation, on the source side, we think about the total mass that we have and the mass discharge. That really sets the duration and the strength that we're going to have to be able to manage with a passive remedy. On the attenuation side, we have these different processes, and Katie talked about some of these. And again, there are rates of those processes, but to turn that into something that you can really think about in terms of a balance, then we're going to have to add these factors of time and distance. So when we think about the knobs that we can turn, so to speak, on the attenuation side, the real knob that the site decisions have to turn is how much space and time are we going to allow for these attenuation reactions to occur. So that's a key point that the site decision makers have to make up front in this transition decision process. Of course, on the source side, the knob that we're turning is how much source treatment or containment do we have to accomplish? How much reduction of that contaminated material do we have to achieve? So between those two knobs, we have to decide, well, what's the right point when we match those and we can let passive remediation take over for us. I'm going to give a case study here. This is from the Joint Base Lewis McChord site. This case study is also described in a manuscript, the Truex et al. 2017 manuscript, and we'll have some references at the end of the presentation that you can look up later. But this is sort of a two-plume system. So the top aquifer here is an unconfined aquifer. There's a source area where there was some source reduction done, thermal treatment and other actions, and then a pump and treat system put in place to contain any residual source to effectively try and cut off the source or the plume from the source. The existing plume in that upper aquifer had a pump and treat system installed at the distal end to contain it and keep it from moving off the post boundary. Now, this is the upper aquifer system, but there's also a lower confined aquifer system, but unfortunately there's also some windows in that confining unit, and one of those windows allowed contamination to move into this confined system and create what we call the sea level aquifer plume. And what I'm going to talk about is the sea level aquifer pump and treat system, and really I'm going to talk about that from the decisions that we made during design of that and installation to decide, well, where are we going to put this system within this overall plume to balance what we can account for with natural attenuation and what we need to contain. How long are we going to operate that, given that we cut off the source and this contamination upgrading will start diminishing? How much do we have to contain that before we can then let attenuation do its thing and reach our remediation goals? So that's kind of a way to look at this. And the important to emphasize here is this was done up front before we started active treatment, because we wanted to put this whole horizon of planning into this overall process. So let's look a little bit at this system. So here's a top view, and here's the plume up here that you see only within the sea level aquifer to start with. You can see that shape, and you see that it kind of makes a turn here, and I'll explain that later. There are some hydraulic reasons why this plume turns, but functionally, what we're trying to look at is there's a zone between the site boundary and the current plume that's an attenuation zone, and we had to decide where to put these pumping wells, which are these yellow dots, and in order to contain this plume behind there, and then also to allow this plume in front of that or downgrading of that pump and treat system to attenuate. So this essentially defined our attenuation zone. So this was the first conversation with the site, was how do we pick that location, understand the attenuation in this zone, and make sure that it'll work both for this remaining sort of bubble of plume downgrading the pump and treat system, and then how will it relate to our decision for how long to pump and treat. So to do that, we did some studies on the attenuation rates that occurred in that zone. And so that's sort of this red oval here. There are attenuation processes that occur there. Some of those are dilution and dispersion and other reaction processes. So we went through that, and if you kind of think about that, if we look at this as just sort of a first order equation, which is this threshold concentration equation, we can think of, we have a goal, a remedial action objective concentration goal. We have some rates that we've now determined, the K factor, you know, what we think we're going to see for attenuation rate. And this time now is really set by this attenuation zone. It's the time for this based on the rate of groundwater and plume movement through this zone and the distance, right? Those two together give us the time frame that we have while this plume is attenuating. And so between those, if you do a quick sort of first order calculation, we would say that if we have that attenuation occurring in this zone, we can leave about 20 parts per billion up in this plume here and still get attenuation to meet our goals at the site boundary. Now that's what we term that back of the envelope calculation. And we had to support that with some predictive modeling estimates, because it's important, just like when you do remedy selection, you have to support defensibly what these decisions for transition will be. So there we really worked on quantifying the attenuation that we had going on in the zone. But we also know that once we install this pump and treat system, we will be able to watch this down gradient plume diminish over time through attenuation, and verify those attenuation rates. So that's this balance between what do we need to know up front to make have good confidence in our decision. And what do we know about attenuation rates and then groundwater movement? So we can use that in conjunction then with verification monitoring to make sure that's occurring. And then fortunately, we can use that then to make some adjustments to how long we run the pump and treat system to ensure that when we turn that off, we will again meet our overall remediation action objectives. So if we go on to thinking about how we look at attenuation processes, for this particular case study site, we had to look at these windows between the upper aquifer and the lower aquifer system. So I've talked about this window that's shown here where the contamination entered, and this red dotted line is the path of contamination. But there's also another window essentially beneath American Lake that allows water to move in. And you can see that in these hydraulic contours where you have this bulge in the hydraulic contour, which is why this plume moves off to the side. And of course that diverts the plume, but there's also water moving in here, which is a dispersion element and a dilution element. There's a mixing going on here, and we used isotopes to help us look at the difference between the isotope signature of the younger upper aquifer water and the lower, older aquifer water, and quantify some of this mixing so that we can include that in our model and have a better confidence that we are understanding and being able to predict the amount of attenuation that would occur. So that's just an example of some of the defensibility we had to build into this. But again, that's an estimate. And so the ace in the hole, of course, was our ability to use the monitoring of that existing plume and its attenuation to make sure we had a good estimate for our future decision. So then when we think about what does that decision time look like, here's a plot where we looked at modeling, predictive modeling, and these two plots here, this is with 20 years of pumping. And so after 20 years of pumping, our residual plume looks like is depicted here. So we have about 30 plus ppb in that residual plume. But then when we looked at that predicted response, we see that at maximum plume extent, the 5 ppb contour would go past our site boundary. So the knob we turn here for active remediation is related to pumping for longer. So we have a lower concentration in this upper plume. Again, when that approached about 20 ppb, similar to what our threshold concentration calculation was, we see that the maximum extent of the plume is well within our attenuation zone. And over time, then this small plume diminishes and we never have an excursion past the site boundary, and we meet our conditions of the groundwater concentration goals within our site boundary. So both of those conditions were met. And again, this was our prediction. We are in the process of monitoring that existing plume to confirm our attenuation rates. And then the knob we can turn based on how that on what attenuation we observe is how long we pump. So those are the sorts of factors that went into having the regulators be involved in this whole process and then agreeing that yes, we have control of this and we're managing that transition effectively and therefore can proceed with moving from an active to a passive remedy for this site. So I've talked a lot about a plume, and we can kind of think about plumes in terms of concentrations, but sometimes it's also important to think about mass discharge. And of course you can think about that for plumes, but another case study within this manuscript from 2017 is the Time Oil site up in Tacoma, Washington. And here is a site where they had pump and treat containing a source, but they knew they had actual source material in this area. So they wanted to apply a treatment. And what they wanted to do, and unlike the previous example where essentially we're identifying a pump and treat time frame and a threshold concentration for a plume, here we now have to identify a mass discharge reduction goal. How much mass discharge reduction do we need in this source zone so that again we can balance what that mass discharge will be when we turn off the pump and treat system to be balanced by the attenuation capacity. So even in that case where they're applying a different sort of treatment and they're thinking about a mass discharge based goal, it still all starts out with setting up what that attenuation zone is, the time and distance, and then identifying what will balance that in terms of what sort of diminishing of this source area is needed so that we will not impact the receptor. at this particular site, then that was done up front before they went into their source treatment processes. And they set, therefore, an interim goal in the ROD associated with this mass discharge reduction goal. And so that is a way now they have a target out there. And over time, they can verify that mass reduction with the pump and treat system. And then after that's off, use those same sorts of wells and monitoring wells to verify what the conditions are for attenuation after they shut down that system. So because they walked through that whole process and defined all these entities for the decision up front, the regulators and all the involved parties were able to agree that yes, this would be a way that they can manage this transition. So I've kind of stressed this idea of setting up these upfront attenuation zones and these ways of doing these calculations, but it's also, I've been stressing this idea of having to verify what's happening. And I want to make a couple comments about that. One is that this verification zone really extends both back into the source or the contained plume area, as well as just down gradient of where that containment or treatment is occurring. And the reason this zone is in this area is because, one, we need to learn and verify what the conditions are in the source zone, so what that mass discharge will be as we start turning off this system. And then we need a zone near enough to that area so that as that, during the first part of that transition, we can look at the concentration and how the plume is evolving and say, is that evolving in a way that's expected based on how we expect our overall attenuation zone to behave? And so that way we have this upfront near-term indicator as to whether or not that transition is going to be successful or not. And that's an important part of how we can verify with the regulators and support a decision so that they know that when we make this transition, we'll be watching it carefully. So we'll talk a little bit about this, and an example I have is at a private site. So I'm not going to show the details of that, but we did essentially exactly this process. At that site, it was a chlorinated solvent site. There's a pump and treat system. We worked to define what the source characteristics were. We looked at, once we turned off that pump and treat system, we looked at the attenuation capacity. We needed the plume that would move out for a certain distance. And that distance is one way to verify. We could look at the distance the plume moved, but we can also look at the attenuation process. So for chlorinated solvents, you create daughter products, and the ratio of the daughter products and parent constituents in the plume also tells us how well that attenuation is working. So we could put some scenarios out there and say, well, if it's working like we expected, we would see the plume move this far in this amount of time, and we'd see this ratio of daughter products. If it was working, say, only 10% as well as we thought in terms of attenuation, then we'd see the plume move at a faster rate and have a different daughter product ratio. So the point here is that there are ways that you can use and look at your particular system to fine-tune your verification process to provide confidence in what's happening over this transition. And that's really where the sort of rubber meets the road, is translating some of these broader concepts that are certainly important in terms of setting the attenuation zone and your transition time frame, but then looking at the defensibility and what sort of technical horsepower do you bring to that to support these decisions. So that's some examples, and I've talked about that for the Fort Lewis example, talked about it here for this private site, but it really gets down to this idea of verification. Rebound testing certainly is another form of verification. And then when you think about that post-transition verification, the reason this zone is smaller than the full attenuation zone is so that you can think about this idea of the possibility for any contingency actions. So those are a couple points about monitoring. And now I'd like to move on a little bit and talk about, well, that monitoring doesn't necessarily always start after you make the transition. You really can start monitoring before the transition so that you understand more about your system and that plume that you're going to essentially transition into that passive period. And so this is at the Hanford site, there's a pump and treat system in play. We're looking at a future transition to a passive remediation with natural attenuation. So during the pump and treat period, we're monitoring the performance, but we're also calculating, predicting from that monitoring data. So the calculations include things looking at things like mass extracted from the different wells, how that relates to our estimates for the amount of mass in the aquifer. We're comparing that to what our predicted values are. And the reason we're doing that is so that we can then, when we get down to thinking about interpreting that for what sort of optimization we need to do, that's not only optimizing the pump and treat system itself, but it's also looking at what did we learn in terms of the conceptual site model? Are there any model configuration updates that are possible that will help us in a way understand the system better as we then can move that understanding into our transition to passive? And then also, what does it mean for our monitoring? Where's the best place to monitor so that we can understand the system as a part of that, both active remedy management, but also our transition management. So now I'll also talk about one other thing that I think is important to consider, and that is this idea that, you know, we've been kind of talking about these plumes as though they're these nice linear cartoon type of plumes with the source area, and here's the plume, and we can think about them that way. And that, of course, conceptually is a good way to think about things, but that's not always the case. And so when you think about something like soil vapor extraction, where your source is in the vadose zone, you may say, well, okay, now I've got a different system. If I'm going to look at what sort of mass I could leave, for instance, in a low permeability zone that I can't effectively extract with soil vapor extraction, I now have to answer this question, well, how much can I leave there so that it's not going to impact my groundwater or perhaps vapor intrusion? But there's different transport going on now. It's not just this simple plume. Now I have to think about vapor transport, which is three-dimensional, and I have to think about mass transfer into the groundwater. And so if you think about that, if we were only had groundwater advection or pore water advection through the vadose zone, that might be a 1D problem, but it's not just the transport in the vadose zone from the source to the groundwater, it's also this flux boundary into the groundwater that has to be considered. So we looked at that sort of process and published some work looking at, well, why is that important and how do you calculate that? But then we also had to look at this three-dimensional vapor transport, because this vapor plume emanating from the source really also controls the flux boundary here based on the vapor concentration. So I just want to emphasize here that while we think about this conceptually, and it's important to do that because that allows us to walk through the process, we have to pay attention to the details of the system. Now that doesn't necessarily mean that you need to know every little detail about the subsurface. You need to consider what are the CSM elements and complexity of that transport. But importantly, you need to say what are the elements that really control transport. So the example for SVE is that we identified a rather limited set of parameters that really control the long-term transport, because that's really functionally what controls the long-term mass flux into the groundwater and the balance with attenuation. While there's other dynamics going on in the short term, those aren't as important for that longer-term balance and ultimately reaching your goals. So you can now get your hands around this problem and solve those contaminant issues without having to characterize every little square centimeter of the subsurface. And so there's some important considerations here when you think about refining the CSM. Yes, it's important, but it's really also important to focus on controlling features and processes, and then identify this idea that you're never going to know everything, but what is a sufficient analysis to allow you to make the decision, just like you always do with any sort of a remedy. You make a decision with some uncertainty, and then how would that play into your verification processes? So with that, I'll just move into some concluding remarks, and I wanted to sort of reemphasize this idea that the current sort of thinking in terms of adaptive site management and emphasis on consideration of this for complex sites really fits well into this idea of organizing the approach for making these decisions between different steps in a remedy, and in particular for this seminar, thinking about the active to passive transition. So that's something that I think sites should consider in terms of how do you apply those adaptive site management approaches within these sorts of individual decisions. I also wanted to emphasize this idea of time and space. It's really important when we transition to passive remedy to upfront identify where that zone is, where we can say, yes, we're going to allow the plume to be within that zone for a certain amount of time, and we can control exposure while the passive remedy applies. And when we define that zone, that enables us now to calculate an attenuation capacity and do that balance between the source and attenuation capacity. If you don't effectively define that zone, then you really can't do that calculation. So that's an important factor. The last couple things I'll mention here is that when we think about that attenuation zone and the time and space, you think about that for a residual plume, and that's sort of one way to think about, well, where's that plume going to move and how's it going to attenuate? But when there's a source present, we also have to think about that in terms of how does that lingering source affect the time frame, or how much extended time contamination might be present. And is that time frame going to be acceptable? Is there a way to diminish that source enough based on the time frames that are desired, or is there going to have to be some sort of ARAR waiver considered? So I think those are things that are kind of additional considerations, especially when a source is present, or potentially when this receptor zone is very close to the plume and there's not much of a downgrading attenuation zone that's possible. Again, another thing to emphasize is that in all of these considerations, we're always going to have this uncertainty when we make a decision. And so this idea of verification monitoring, but also of contingency actions, I think is important. And that's a well-established sort of approach back in the M&A directive back from 1999. They recognize this. When you make a decision for M&A, there are uncertainties, and therefore you consider what sort of contingency actions you might have. Same thing applies for active passive remedies transitions. And so I think that's something to keep in mind and to dovetail in with that verification monitoring. And the last thing I want to mention is that we've talked a lot about the near-term monitoring and how that's really important to verify that the transition is appropriate and that things are going as expected. As you move into the longer-term phases of monitoring, of course, your type of monitoring can change. And so part of that might think about, well, what are the overall conditions? Are the groundwater flow conditions staying the same over the long term? Are the overall driving conditions for contaminant moving staying the same? And you can kind of balance monitoring of those conditions with how much monitoring you need of the actual contamination to develop a long-term strategy once you verify that you're on the right path. So I think those sorts of concepts are important. So hopefully what we've been able to show you is, again, the context for how we can think about active passive transition and some of the resources that are available. I've showed you a couple of case studies and some what I consider some important considerations for how we go about this process. And then I think also I tried to emphasize that once you get to your specific site, the complexity of that site will really drive you to the type of analyses that are needed. And so that's really moving across that whole spectrum that we try to think of in RemPlex, the Center for Remediation of Complex Sites, where we think not only of the broad context, so how do we set our context for decisions, but then how do we also apply the detailed technical approaches that help with the defensibility that's necessary to support those decisions and the implementation of the remedy itself. So again, hopefully you've gotten some appreciation for this overall process and some resources and tools that you can think about. And so like I mentioned, when this presentation is available, there'll be a reference list at the end of this if you want to check out any of the references that we provided in our presentation. But with that, I'd like to thank you for listening for both me and Katie, and we'd be happy to answer any questions that you might have.
Great, thanks, Katie and Mike. We do have a question coming in. First, are there any methods or resources you can share to estimate mass flux from low permeability sediments?
So yes, there's been actually quite a bit of work on that in this sort of matrix diffusion element. And so there's a new RemClor version that helps, at least from a numerical estimation standpoint, estimate some of those numbers. There have been attempts to use things like high resolution characterization, so you can better understand the relative concentrations between low and high permeability zones. And there's been applications of things like passive flux meters within different zones of the aquifer that have helped with that, as well as rebound testing. And so rebound testing gives you a little bit of a broader picture of that, but it still is important because it tells you, well, what did you see when you had, for instance, a pumping well with a high flux through the high permeability zone? What sort of concentrations and mass flux did you observe? And then you can shut off that pumping well, look at the lower velocity values, and that can also give you some information. So I think there are some tools out there. The ITRC has some really good resources on that, as well as some of the tools that Katie had presented earlier. And there are some references that you can look at when this presentation is available. But it is a good question. That lingering source and matrix diffusion is of major concern for these sorts of transitions. So having a way to characterize that is important, but I think the industry has really matured in its way of looking at that. So hopefully that gives you some pointers as to places to look.
Great, thank you. One question I had, Katie, you mentioned in the beginning that active treatments can be more costly than passive. And so I was wondering if you could talk a little bit about what factors influence that cost.
Sure. So I don't, have specific numbers, but in general, I mean, an active treatment is going to require constant operation. You're going to have the maintenance associated with that, and all of those elements that are really, the active component of this. Whereas passive, it's much more on that monitoring side of things, and you kind of let the natural conditions kind of take back over, and so you don't have as many elements that you really have to support when you've moved over to that passive side.
Got it, thank you. All right, one other question that's coming through. How do you determine the amount of data needed to support a decision to transfer or to transition, from active to passive remediation? Katie or Mike?
Well, so I'll just start with that, and Katie, if you want to chime in, one of the things that I tried to emphasize in the talk was this idea that I think you need to think about the defensibility, essentially, is what that question is about. How much data do you need, as similar to the type of defensibility that you use up front when you're doing the RIFS process and you make a remedy selection. And so at that point, the RIFS is conducted with a certain amount of information and analysis that says, within reasonable prediction, we believe that this remedy will meet our goals. And so you apply that same sort of logic at the transition point where you say, well, we have to collect enough information so there's confidence by the decision makers that they say there's a reasonable certainty that our transition will lead to a passive remediation condition that will eventually meet our remedial action objectives. So it really gets down to uncertainty management. And so I think the way to think about that is the same sort of uncertainty management you apply earlier in the circular process at that RIFS stage. You also apply at this transition process. The benefit is that at this transition, you've had however many years of active remediation, and in many times remediation is a really good characterization technique. And so it's really important, and that's why I emphasize the need to mine that active remediation timeframe for information that helps you understand the system, and that will give you a better understanding that leads to more confidence. So I think you're always better off in the transition decision than you are at the upfront remedy selection stage, but it's important that you pay attention to that data that are available, and then use it to, again, manage the uncertainty, and then with any remaining uncertainty, manage that through the verification monitoring that we talked about that helps verify that, again, that transition is proceeding as everybody had hoped it would.
So the only thing that I would add on that is a lot of those existing tools do have the uncertainty kind of built into that to kind of give you an estimation as well. So that's just another kind of element that I wanted to throw out there.
Great, thank you. Well, I want to thank everyone for joining our seminar today. Just a reminder that the seminar will be archived on the RemPlex website. We look forward to presenting our next seminar on integrating key capabilities for the remediation of complex sites on October 27th. And we encourage you to sign up for the RemPlex newsletter by sending an email to remplex@pnnl.gov and to join the LinkedIn group using the link in the chat box. There's also a link in the chat box to take an optional RemPlex survey. And so thank you again for joining us, and we'll be following up next week with an email with the link to the seminar recording. Thank you. Thank you, Mike. Thanks, Katie.
Thank you.